Good day, everyone. Before we get started, I'm taking your question. Do you have any question? Okay, so no question, no problem, right? You can talk to me during the breakout session when I finish the lecture. So today I'm gonna get started on the chapter 2, right? Okay. All right, so we're gonna take a look at the introduction to the exponential functions. All right. So chapter 2 is on the exponential functions, also the application, right? By the time we get to section 2.3, it's application. So we're going to take a look at some of the applications of the exponential function. All right. So section 2.3. So we're going to take a look at the properties of exponents, in terms of simplifying exponential expressions, and also solve exponential equations. And we're also going to take a look at how to sketch the graph of exponential functions in these two sections. And exponential functions basically in the form of, just show you the general formula, f of x equal to n raised to x power. Here, n is the constant. And then x is what we call the exponent. Just like what you learn in algebra course, we still stick with the same notations. And we actually, in chapter 1, we take a look at some of the polynomial functions like f of x to the x cubed. But the most popular one is mx plus b, right? That's a first degree polynomial functions, and that's third degree polynomial functions. And typically, the exponential function will appear in this form. Will appear in f of x equal to 3 to the x. So basically, we looking at the base as 3, a constant. So 3 here is what we call the base. And x is what we call the exponent. So for any exponential function, two most important element is the base and also the exponent. And the base determines the overall trend of the exponential function, whether it's a growth model or decay model, right? So basically, for most of the exponential functions, we have two types, either a growth model, meaning it's constantly growing. Okay, so this is the first one. Second one is called decay model. Decay meaning it's constantly decreasing, right? Or becoming less and less, right? As the time goes by. So exponential function has variable in the exponent, not in the base. Okay. Variable in exponent, right? So variable is in exponent. The base is always a constant, right? Base is always a constant, typically a natural number. All right, so let's take a look at general form. F of x equal to n to the x. Here n is greater than 0. So that's base. So make sure base is greater than 0. Base cannot be 0, right? N can never be 0. Okay. If n is 0, then it's not an exponential function, it's a constant function. Okay. All right, so now let's review some of the properties in terms of the multiplying, dividing, subtracting, and adding those exponents, right? So let's take a look at those basic properties. The first one is when you multiply two exponents with the same base, right? Two exponents, same base. That's very important. We basically just keep the base a, and you add in exponent, right? You sum up a, x and y, adding x and y, adding those two exponents. Okay. So multiplying two exponents with the same base, we basically just add in the exponent, keep the base. And that's first rule. So for example, a very simple example is, let's say you get a to the second power times a to the third power, then you keep the base a, then add in 2 and 3, you get a to the fifth power. That's how you apply this property. Okay. And also we have an exponent raised to another exponent. So you multiply the inner exponent by the exponent outside. So it becomes a raised to xy power. And for example, so you multiply x and y to become a new exponent. For example, let's say you have a to the second raised to third power. So right now, we basically just keep the base a, and you multiply 2 and 3. It becomes a to the sixth power. Okay, so it's a to the 6. Notice that it's different result, right? From the multiplying of exponent raised to another exponent is totally different. And we also have distributive properties here. And let's say we have two variables, a and b. They have the same exponent. Now you can distribute variable exponent x to both variables. So it becomes a to the x and then b to the x. For example, let's say we have a, b raised to fifth power. Now it becomes a to the fifth times b to the fifth. Okay. So that's how you apply the distributive properties in terms of the exponent. And we also have a, let's say we have a quotient inside parentheses and raised to x power. Again, we distribute the power to the top and bottom, to both the numerator and denominator, and we get a to the x over b to the x. And for example, let's say we have a over b to the fifth power. Now you can do distributing both a and b, right, with the power to the fifth. So it's a to the fifth over b to the fifth. Okay. And we also have a dividing to exponent. For example, like a to the x over a to the y. So again, keep the base and then subtracting the exponent. So it becomes a base remain as is, and then x minus y. So for example, let's say we have a to the fifth over a to the third, right? Same base, keep the base. Now using the bigger power, subtract the smaller power, keep it on top. So it becomes a to the second power. Okay. All right. Also, sometimes you may encounter negative exponent. So typically you look at it as a fraction, right? And then you flip the negative power to the denominator and it becomes a to the x, right? So for example, let's say we have a raised to negative second power, then it becomes 1 over a to the second power. Okay. So when you flip to the bottom, and the power becomes positive. And also, what if we have 1 over a to negative x? It becomes, and you flip the negative power to the top, it becomes positive power, a to the x. Okay. So for example, let's say we have 1 over a raised to negative second power, then it becomes a to the second power. All right, so the very last one is a raised to x over y power. Okay, so similarly, you can distribute it. So it becomes square root of a to the x. So the power on the numerator becomes the power to the x, and denominator becomes the root. So this is ax root y. Okay. So for example, let's say we have a 3 over 2, right? Now it becomes a cube and taking the square root. Okay. So that's how you're converting the exponent with the fraction to the radicals. And now let's take a look at some of the examples, how we solve all of this. Okay. And let's solve some of the, applying these properties, solve some of the actual problems. Here, the first one is multiplying two exponent with the same base 2. So keep the base 2, add in the exponent 2 plus 3. And then this becomes 2 to the 5th power. 2 to the 5th, we know this 2 times 2 times 2 times 2 times 2. And you can just put into the calculator, you get 32. Okay. Right. That's first one, applying the multiplication property. And then we have again, one more time, we have multiplication property. So 2, adding exponent 2 plus negative 6. So this is 2 raised to 2 minus 6, 2 raised to negative 4, right? So according to the other property, so it becomes 1 over 2 to the 4th. Flip to the bottom, it becomes a positive exponent. So this is 1 over 16. 2 to the 4th is 16, 1 over 16. And the third example, we have an exponent raised to another exponent. Keep the base, multiply 3 and 2, you get 6. So it's 2 to the 6. So 2 to the 6 is 64, right? It's 4 times 4 times 4, 64. Okay. Any questions so far? All right, let's move on. Okay, so this one, we have an exponent raised to negative power. So in order to get rid of this negative sign, you will use the reciprocal of 2/3, which is 3 over 2. So using reciprocal of 2/3, which is 3 over 2 and raised to the 3rd power. Now we get rid of the negative exponent. And from there, we distribute the power 3 cubed over 2 cubed. Okay. And 3 cubed is 27. 2 cubed is 8. So the answer is 27 over 8. And this one, now if you look at it, you can just apply the rule, right? So using the power 7 minus 9, so we end up with the 3 raised to negative 2nd power. Then from there, we use 1 over 3 to the 2nd power. That becomes 1 over 9. All right, and this one, make sure you notice that the base must be the same, and here the base is not the same, so we have to do a little conversion here. So 2 to the half remain as this, but we know that we can convert 8. 8 equal to 2 times 2 times 2, which is 2 cubed. So now 8 becomes 2 cubed to the half power. Right? Now we turn into the same base. So 2 to the half times 2, 3 times half is 3 over 2. Now you see the same base. So we keep the base 2, we're adding half and then 3, adding them 3 over 2. So now the fraction, they are like fractions. So end up with a 2, 4 over 2. That's to the 2nd power. So it's 2 to the 2nd power. That becomes 4. So the answer is 4. All right. So sometimes you got to be flexible, and then try to use some of the other properties to convert it. Now let's take a look at how to solve some exponential equations. Right? And still, we're going to use some of the properties. So for example, like this one, 5 to the x equal to 125. And right here, base is 5. So it's 5 to the x. And we know 125 is 5 times 5 times 5, which is 5 to the 3rd power. Okay. Now, as you can see, we turn into the same base. So according to the linear equation, so when the exponent with the same base, then the power must be the same, right? X must be equal to 3. Okay. So converting both to the same base and then equalizing the exponent. That's how you solve it. And second one, you see the base are the same already. So that means the power must be the same. X minus 1 must be equal to negative half. So x minus 1 equal negative half. Then from there, you're just adding 1 from both sides of the equation. Then x equal to negative half plus 1. 1 is equal to 2 over 2. So it's half. Okay. All right, so this is very simple exponential equations. We may have a little bit more complicated one like this and that one. So first of all, in order to solve this, you see this base is 2 on the right. On the left, we know that 8 is equal to 2 cubed. So it's 2 cubed raised to x power equal to 2. So now it's 2 to the 3x equal to 2 to the first. So put back this invisible 1, right? You can put it back. And now same base again. And power must be the same, 3x equal to 1. And from there, we divide 3 from both sides equation. Then x equal to 1/3. All right. Any suggestion on this one? Any idea how to solve the other one? A to the x equal to 4. Nope. All right. So very similar idea, right? So we turn the a as 2 cubed. And then 4 becomes 2 squared. Now you see same base, right? So 2 cubed to the x, and then 2 to the second power for 4. So now again, 2 to the 3x, multiply 3 and x, get 3x equal to 2 to the second. Now same base again. Now very crucial, right? We want to make sure we have the same base. And the power must be the same, 3x equal to 2. Now from there, we just divide 3 from both sides of the equation. And we got it, right? So x equal to 2/3. So that's how you solve a little bit more sophisticated, exponential equation. Now let's look at some other, a little bit more complicated ones. So this one, 1/3 raised to x equal 27. Now, as you can see, this base, so we can turn 27 as 3 cubed, right? So, and we know that the other base is now 3. So what we can do is reciprocal this, right? Use a reciprocal of 1/3, which is 3 over 1. Now the power will become negative x. Okay. Using the reciprocal, the power becomes opposite. And 27 is 3 cubed. Now we get 3 to negative x equal 3 to the third power. Okay. And then from there, same base again, very crucial. Negative x equal to 3. Now we could multiply both sides of the equation by -1. So we get x equal to -3. Okay. All right. And this one, we have x raised to 1/3 equal 27. So now what we can do is multiply both sides of the equation. So raise both sides of the equation to third power, right? And then we can simplify. So using this property to get rid of the 1/3 power, 1/3 times 3 becomes 1. So x raised to the first power and 27 to the third power is fairly large number. Let's see what that is. 27 to the third. It becomes 19,683. So x value equal to 19,683. So raise both sides of the equation to the same power, and we end up with the correct answer. And now let's look at this one. X raised to 3/4 power equal to 8. So right here, we use the reciprocal of 3/4, which is 4 over 3. So raise both sides of the equation to 4 over 3 power. Okay. So now 3/4 and then 4 over 3, they are reciprocal. Once you multiply both exponent, it becomes 1. 3/4 and times 4 over 3 is equal to 1. 3/4 times 4/3. You cancel all the numbers, it becomes 1/1. It becomes 1. And here a raised to 4/3 power. So here we just gonna raise to the 4th power and take in a radical, cubic root, right? So it's cubic root a to the 4th power. And then what you can do is, one thing you can do is you can just put this a raised to 3/4 power into the calculator, get a result directly. The result should be 16. Or you can just take in the cubic root of this, right? So it's easier, just use a raised to 4/3 power, and that becomes 16. Okay. If you do it directly, I can also show you another way of doing this. Is this. So 2 cube. So a becomes 2 cube. So here this becomes 2 cube raised to the 4th power and cubic root. And this becomes cubic root of 2 to the 12th power. Now we can just do 2 using the power divide by the exponent, and it becomes 2 to the 4th power. And 2 to the 4th is 16. So either way you like, right? You can input into the calculator directly or into the Excel directly, you get 16 right away. Or you can use the algebraic transformation to get a result 16. Okay. And this is not considered as an exponential equation, right? Because the variable is not in the base. It's not in the exponent, right? Variable is the base. So it's not an exponential equation. Now, just one more thing, and then before we end the lecture, today we're not going to do the whole lecture. I'm still going to give you time to work on your project. So let's go over this one and then give you some idea how to graph this exponential equations, and then we're going to go to the project. So the general form of the exponential function is that. Okay. And now we get a g of x equal 2 to the x. So the base is 2, right? N equal to 2 and then x. And right here, we try to come up with some order pairs. Okay. So go here. So here we're going to take a look at, we pick some x values, right? So x value from 2 all the way to -2 is decreasing by 1, right? So right here, we picked all the x values, and then we want to find out the y values. So first one, you want to find out what is G2, right? When x equal to 2 means we look at the G2. So 2 to the 2nd power, that becomes 4. Okay. So the first number is 4, right? Second number, G1 is 2 to the 1st power, that's 2. Okay. And then G of 0, that's 2 to the 0 power. Any number raised to 0 power is 1. So this is 1. So now G -1 is 2 raised to -1st power. It's 1 over 2 to the 1. To the 1st power, it's half. You can write 0.5 if you want to, since it's you can convert it easily to decimal number. And G of -2 and 2 raised to -2 is 1 over 2 to the 2nd power. That's a quarter. And a quarter is 0.25. As you can see, okay, as we go by the numbers, anytime, you know, when the number decreases by 1, then it becomes half as much, half as much, half as much, half as much. Okay. So this is a very clear pattern, right? Appear in exponential functions every time when the base is positive. In this case, +2, and then when the power decrease by 1, then it shrink by half, right? Shrink by half. If you want to put into the increasing order, let's say, you will also see a very clear pattern here. We start with -2, -1, 0, 1, 2. Now -2, that's a quarter. -1, that's half. 0 is 1, 1 is 2, 2 becomes 4. As you can see, when it's in the increasing order here, every time we add in 1 to the exponent, then the y value is double. So it's doubling here, doubling. If you want to move forward, let's say 3 here. So g of 3 equal to 2 to the third power, that becomes 8. And again, it's 8, right? Doubling. So the very important characteristics of exponential function when the base is greater than 1. So when n is greater than 1, so we have a growth model, right? So this is growth model, meaning when x increases, then the y value increases. And this particular case is doubling. Okay. Right. So that's, and then in terms of graphing this, you just have to plot in all these order pairs, right? So we have all these order pairs. So just make it -2 quarter, -1 and a half, 0, 1, 1, 2, and 2, 4. Let's plot 5 order pairs, right? So you just need to plot those 5 order pairs on a Cartesian system. So the x values is from -2. Okay. Start with -1, -2, -2, -1, 0, and 1, 2. The y value all the way, the highest is 4, right? So it's 1, 2, 3, 4. That's good enough. And the minimum is quarter. Okay, so we start plotting this. So -2 corresponds with the quarter. So this is half, quarter is here. Let me use a different color. Quarter is right here. Okay. And the -1 is half. So this is half. That's a quarter. So half is here. Then from there is 0, 1. So we call it the y-intercept. And then 1, 2. And then 2, 4. And as you can see, for the exponential function, it's not a straight line. It's like the curve, right? It's a smooth curve. And right here, from left to right, since the base is greater than 1, then it's increasing from left to right. Okay. So from left to right, it's increasing. Increasing meaning it's growing, right? Increasing from left to right. And also, x-axis is what they call the asymptote, meaning the graph of function gets infinitely close to x-axis, but never touches it, right? Just getting closer and closer, but never touches it, because no matter what power we have, right? Let's say 2 raised to a million power, negative a million power, it becomes 1 over 2 to the million power. It's still, right? It's not equal to 0, okay? But it's getting closer to 0. So in this case, on the left-hand side, the function is getting closer and closer to x-axis, meaning the y value is getting closer and closer to 0. And we call this x-axis asymptote. Asymptote is a line or curve. The graph of function gets infinitely close, but never touches it. All right, any question on the graph? We're basically just plotting those 5 order pairs to get a graph. I'm going to show you how to do this in Excel really quickly. Now, another example could be this, right? So I'm going to do this. I'm going to go the other way. I show you the clear pattern here is I'm using the increasing order, meaning we start with -2, -1, 0, 1, 2. Okay. So I'm using the increasing order here from -2 all the way to 2 to show you the clear pattern. So first one is h of -2. So here the power become -2. So I get 3 raised to -2nd power. So it's 1 over 3 to the second. It becomes 1 over 9. Okay, so this is 1 over 9. Now h raised to -1 is 3 raised to -1st power. So it's 1 over 3 to the first. It's 1/3. Okay. And then h of 0 is 3 to the 0 power becomes 1. Any number raised to 0 power is always 1. Okay. And then h of 1 is 3 to the first power, that's 3. Okay. And then h to the second power is 3 to the second power, that's equal to 9. Now, if you look at this number, as x value increased by 1 unit, it's tripling, right? It becomes 3 times as much, tripling, tripling, tripling. So as obviously next, if you want to predict next number, should be triple of the previous number, 27, without calculation. So that's how we utilize this base to determine. So this base determines how fast the exponential function grows, right? In this case, it's tripling because the base is 3. Base is 2, doubling. Base is 3, tripling. So in terms of graphing this, we could just simply quickly graph this, right? Using 5 order pairs. So the order pair is -2, 1/9, -1, 1/3. Zero, 1, 1, 3, and then 2, 9. So here we start with -2. So then -1, -2. 1, 2 on the right. We need 9 units on the horizontal vertical axis. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And we start plotting those order pairs. -2, 1/9. So it's very, very close to 0 here. And I'm using different color. Okay, so right here. And then the second order pair is -1, 1/3. So it's 1/3 of this 1 unit here. So it's here. And then after that, 0, 1, 1, 3, and 2, 9. As you can see, it's growing a lot faster. 1, 3. So you connect all those 5 points, extend the both direction, then we get a line, right? Here we go. And as you can see, this curve is more steep, meaning it's increasing from left to right, but it's increasing much faster compared to the previous one. So if you put both together, you can see it's increasing much faster because it's tripling compared to doubling from the previous one. If you put both together, okay, I'm gonna show you how to do this. I'm gonna keep this. Let me show you a very good resource you can use. Share the screen with you. Okay, if you go to Google and then type in this decimals, right? That's decimals graphing. You can actually graphing both of them together. Use this platform. So you type in f of x equal to 2 to the x. Okay, so this is 2 to the x, and then f of x, g of x equal 3 to the x. now X. Yeah. As you can see, right, this increasing a lot quicker. So the blue one is 3 to the X, the red one is 2 to the X, and this is more steep, right? Meaning when the base is bigger, it's increasing at a much faster pace on the high end. Okay, and it's very easy to graph together in this platform. It's called Desmos. Now let's open Excel. Let me show you how to graph this in Excel. Okay, all of you guys open Excel. Okay. Let me share the screen with you. How to graph this. Okay, here we go. So let's first of all graphing f of x equal to 2 to the x. Okay. All right, so we need two columns, right? X and f of x. Okay. And we need 5 order pairs. If you want more order pairs, no problem. But let's do 5 order pairs, just like the other one. And I format the table really quickly. So let's start with the -2, -1. Okay, now I'm gonna just put in a couple numbers. Now I'll just use this to create all the rest of the numbers. Use the pattern to create it. So now that we need to find out this, right? The value of that. So base 2 raised to this power, right? Okay, that should get a result 1 over 0.25. Okay. And then here you go. Get all of them. And as you can see, this is doubling, right? 0.25 times 2 becomes 0.5. 0.5 times 2 becomes 1. 1 times 2 becomes 2. 2 times 2 becomes 4. If you want to have more, okay, if you want to make a prediction about this, right, highlight that, drag it, okay, you can get a couple more. And here, just highlight the entire cell, you see, doubling, right? So that's how we verify this. But since we only need 5 order pair, that's fine, right? So you just highlight that, the entire table, and go to insert. Now go to scatter plot, right? Again, we just need this, need the graph itself, and then just make it slightly smaller. So you can modify this. So now let's go back. So this is the graph of this f of x. I'm gonna put it on the side and maybe make it slightly smaller so you can see better. Okay, so now it's slightly smaller. And in terms of putting the exponential, plotting this point, you need to go plus here. You see, click on plus sign. Now go to trend line. Go to exponential, right? Pick the second one, you get an exponential. Or maybe even better, click on more options. And now let's work on the exponentials. And you can just, okay, and then you basically just plot those 5. If you want to put in solid line, you can do that. Okay. Transparency, you can modify all of this stuff. Okay, you can use different color to curve it. A lot of things you can do here, right? Shadow, glowing, soft edges. Okay. Then we basically just get this exponential function. Okay, so that's how you graph it. Okay, using the 5 order pairs. And let's graph one more, right? Okay, let's go. Put back exponents. Okay. Now up here, if you want, you can pick design here, right? Different designs available up here. Pick design, and it becomes solid line, solid curve here. Okay. So that's one of them. And let's graph one more, right? G of x. And g of x equal to 3 to the x. So basically, you can easily graph any exponential function here. I'm going to copy the entire table here, since we're going to reuse it. Okay. I'm going to delete all these y values, right? The only thing I have to change is just base is 3, base to this power, B11. Do one of them. Now you can just drag it. Okay. And then tripling. You still see tripling. What if you want a fraction instead of a decimal? You go to format cell, and here you put in a fraction. Yeah, up to 1 digit. Good to go. Okay, so it's 1/9, 1/3, 1 and 3, 9. Tripling, right? You multiply the previous number by 3, you get the next number. 1/3 times 3 becomes 1. 1 times 3, 3. 3 times 3 is 9. So now again, we graph this. So insert, and here go to this. Get a scatter path first. Now let me just reshape it. You can just put a cursor on the bottom right hand corner and then resize it. Make it smaller graph. And again, put it on the side. Then we can just pick a design, right? On top here, you can pick any design you want, right? Let's say I want to pick this design and then go back here, plus sign, and go to more options, click on the exponential, right? Exponential function. So fill in the exponential model here. Okay. Yeah, that's basically how you graph a exponential function using Excel. Any question on this? Okay. All right, so basically you can finish the first 2 projects. Okay, and then also I'm gonna put you guys in a breakout room. So if you have any question, you can talk to me. I'll try to help you out. I also post these 2 graphs. I post this solution in our Blackboard course, so you can use it as a reference. And then also I will post a project number 3. It's about the first couple questions about graphing the exponential functions. You can start working on those if you finish the first 2 projects. I'm posting the Excel project number 3 right now. Okay, so I guess I will put you guys into the breakout room right now, and talk to me if you have any question.